Hi everyone, this is Mrs. GA, and today we're going to cover the basics of rational functions. Alright, so we're going to start by looking at our parent function, which would be 1 over x, and we're going to look at what the graph looks like and kind of talk about why some of these special characteristics happen. So the graph for a rational function looks like this. It has a vertical asymptote. In the parent function, it has it at x equals 0. It also has a horizontal asymptote at y equals 0. So I want to talk about why this is happening. So since x is in our denominator, we have a restriction. That restriction is that x cannot equal 0, so that creates this vertical asymptote. Now the horizontal asymptote exists because if you look at this function and you start plugging in values, you can plug in larger and larger and larger values. Say for instance you plug in 500. You would reach 1 over 500, which is extremely small, and it gets really, really close to the x-axis, but it never quite touches it. And the same thing for negative values. If you plug in negative 500, negative 1 over 500 is very, very, very close to the x-axis, but it never reaches it. So no matter what you plug into x, you will never quite reach 0. So that's why this asymptote exists. And then from there you have a graph that looks kind of like this. So it looks like a hyperbola. And then of course, you could always make a t-chart to get a more accurate graph. So our domain and range are both restricted. Our domain is going to be everything except for 0. So negative infinity to 0 or 0 to positive infinity. And our range is the same, everything except for 0. So negative infinity to 0 or 0 to infinity. So this is the basic graph of a rational function. And then today we're going to be talking about how to find x and y intercepts if they exist, and we're going to talk about how to find these asymptotes if they are somewhere else other than at 0. And then we're also going to be graphing these with transformations. All right, let's start out by finding the x and y intercepts of these two functions. So for the x-intercepts, we want to know when y is equal to 0. And so I'm going to ask myself, well, when is a fraction equal to 0? And the answer is when the numerator is equal to 0. So I'm always going to start by factoring these completely. So x plus 3, x minus 3, and I will factor the denominator as well. And I'm going to make sure that I can't simplify it at all. And now, like I just said, our fraction will turn to 0 when our numerator is 0. So to find x-intercepts, I'm going to set my numerator equal to 0. So I'll say x plus 3 equals 0, x minus 3 equals 0. So I see that I'm going to have two x-intercepts, one at negative 3, 0, and one at positive 3, 0. Okay, I know that I can find the y-intercept of any function by substituting x with 0. So you can do that either in the factored form or this form. So I'm going to go to the original form. So if I replace, so again, we're finding the y-intercepts. So if I replace x with 0, in my numerator I'm left with negative 9. And in my denominator, I have negative 4. So my y-intercept is going to be at 0, 9/4. There you have it. So remember, to find the x-intercepts, you set the numerator equal to 0. To find the y-intercept, you set x equal to 0. All right, let's try this one. So I'm going to factor this. I'm going to try to factor whatever I can. Okay, so for this one, again, we are going to find the x-intercepts by setting our numerator equal to 0. Well, since I don't have any variables in my numerator, I can determine for this one that there are no x-intercepts, which must mean that I have an asymptote at the x-axis, which we will talk about in a little bit. And then for the y-intercept, remember we're going to set x equal to 0. So I'm going to do this in my original equation. My numerator is 2. My denominator is -4. So my y-intercept is at 0, -1/2. Okay, so now we're going to be sketching graphs of these rational functions using transformations. So rational functions follow the same transformation rules as any other function we've talked about so far. And then we are also going to consider the x and y intercepts as we graph these. And just so you know, the asymptotes from our parent function are going to shift in the same way that our graph would. So you will shift asymptotes left, right, up, or down, just like any other part of your graph. So if I look at this and I compare it to what my parent function was, I see that I'm going to have two transformations. I see that I have a vertical stretch by a factor of 2. And that's because I've multiplied my entire function by 2. Remember, in the parent function, it's 1 over x. And then you'll also notice that grouped with my x, so since it's grouped within the denominator, I know that this is going to be a horizontal shift. And remember, horizontal shifts always move in the opposite direction that you think because it's x minus h. So this -3 is going to be a shift to the right 3. So not only is my graph going to shift to the right 3, but so is my vertical asymptote. So remember, my vertical asymptote for the parent function is at x equals 0. So now it's going to be over here at x equals 3. So that shifts to the right 3. Now a horizontal asymptote, it's going to remain at 0 because I didn't shift up or down. And then I'm going to try to sketch the rest of my graph. So I can look for maybe a y-intercept. So if I set x equal to 0, I get y equals -2/3. So I know it's going to be right here, which tells me I'm going to have a graph that looks like this. And then that means the other portion will always be opposite. And notice for this one, I don't have any x-intercepts, and that's because I have that asymptote here, and also because I don't have any variables in my numerator. All right, so let's look at this next one. So this is not in transformation form, so we're going to need to rewrite it in a way that makes it a little bit easier for us to interpret. And we can do that with just basic long division. So I'm going to actually do 3x plus 5 divided by x plus 2. So 3x divided by x is 3, and then I'm going to multiply, so I get 3x plus 6. And then I'm going to subtract, and I'm left with -1, which is my remainder. So when I go to rewrite this, I'm actually going to write the remainder first. I'm going to say -1 over x plus 2, and then plus 3. And I can use this to help me interpret the transformations that are happening. So the first thing I notice is that I have a vertical reflection because of this negative, which means it's going to reflect over the x-axis. And then that x plus 2, the plus 2 next to the x tells us to shift left 2. And then this plus 3, since it's being added to the entire function, it will be a vertical shift. So I'm going to shift up 3. So if I go to graph this, I'll graph it down here. This time I'm going to have a shift in both my horizontal and vertical asymptotes. So my vertical asymptote shifts to the left 2, so we'll put it here, and we'll call this x equals -2. My horizontal asymptote shifts up 3, like this. So I have an asymptote at y equals 3. This isn't drawn to scale at all. The vertical reflection suggests that instead of having a graph here and here, I'm going to have a graph here and here. However, we can confirm that by finding our intercepts. So I see that I am going to have an x-intercept at -5/3, which is going to be right here, roughly. And then I see if I replace x with 0, I have a y-intercept at 5/2, which is a little less than 3, so it will be right here. So that is a way for us to confirm that our graph does fall in this little quadrant, and that means the rest of my graph will reflect onto this side. So remember, just by knowing how to find the x and y intercepts, and then by understanding your basic rules of transformations, you should be able to get a pretty good sketch for a lot of these functions. Okay, so go ahead and pause the video and see if you can graph these two functions. Again, make sure you're using transformations and you're considering the x and y intercepts. Okay, go ahead and check here. So in our first one, we see that we have a vertical stretch by a factor of 3 and a shift to the left 1. So our vertical asymptote was shifted, and then our graph falls here and here, and this is our y-intercept. We don't have any x-intercepts. For the second one, you had to do a little long division, giving you the function 3 over x minus 2 minus 1. So that means that I'm going to shift to the right 2, so that's why my vertical asymptote shifted, and down 1, shifting my horizontal asymptote. And then I see that I have an x-intercept at 5 and a y-intercept at negative 5/2. So our graph looks something like this. Okay, the last thing we're going to talk about is how to find asymptotes of rational functions without using transformations. So it's important to have other ways to find these asymptotes. So the vertical asymptotes are pretty straightforward to find. Vertical asymptotes will always occur at restrictions. So we know that restrictions happen when our denominator is equal to 0. So if you set your denominator equal to 0, you should be able to find your vertical asymptotes. One thing to point out, if you have what's called a removable discontinuity, meaning a factor that cancels out when you simplify, we still have to remember that that was a restriction. However, instead of creating a vertical asymptote, it's actually going to create a hole in your graph. So you're still going to want to make note of it, so you include it in your graph, but it's important to know that it won't make a vertical asymptote. To find horizontal asymptotes, we have 3 different cases, and these 3 cases depend on the degree of the numerator and the denominator. So we're going to assume that n is the degree of our numerator and m is the degree of our denominator. So the first case is, what happens if n is less than m? So anytime you have a scenario like this, you are always going to have a horizontal asymptote at y equals 0, which is the x-axis. The reason why this happens is if your degree in the denominator is larger, and imagine you're substituting values, you're going to be dividing by an extremely large number. And if you're dividing by a really, really large number, you're going to be approaching 0. Now, the second case is what happens if the degree on the top and bottom are equal. So anytime you have a scenario like this, you're going to have a horizontal asymptote at the ratio of the lead coefficient. So see that A is the lead coefficient of your numerator and B is the lead coefficient of the denominator. What's happening here is that if you're plugging in extremely large numbers, like you're plugging in 100 or 1,000 or even 1,000,000, essentially the numerator and denominator, everything's going to cancel out except for these lead coefficients. So that's what your graph is going to approach. And the third case is, well, what if the numerator degree is larger than the denominator degree? So anytime you have this case, you are not going to have a horizontal asymptote, because if your numerator is increasing faster than the denominator, you're just going to approach infinity, which again means you don't have a horizontal asymptote. However, there is one exception to this. Well, it's a more specific case. If n is exactly 1 more than m. So if the degree on the top is 3 and the degree on the bottom is 2, then we are going to have what's called a slant asymptote. Okay, so it's not a horizontal asymptote, but it is an asymptote that we can define, and we can make the equation of this using long division, which we'll talk about briefly today and revisit later on in this chapter. Okay, so let's see if we can use those rules we just talked about to find the asymptotes, both horizontal or vertical, of the following functions. So remember, I like to always start with the vertical asymptotes because I think they're a little bit easier to find. We find our vertical asymptotes by looking at our restrictions. So in this case, I see a restriction at 1. So my vertical asymptote will be at x equals 1. And then remember to find the horizontal asymptotes, we compare the degree of the numerator and the denominator. So since the degree of the numerator and the denominator in this case is equal, our horizontal asymptote is going to occur at the ratio of the coefficients. So my lead coefficient on top is 2, on the bottom it's 1. So that means I have a horizontal asymptote at y equals 2. So those are my two asymptotes. Okay, let's look at this next one. So you can guess, just like most of the problems we do, we're always going to want to start by factoring just to see what we have. So in my numerator, I have 2 times x minus 2. In my denominator, I have x plus 1 times x plus 1. Okay, so nothing cancels out or simplifies, meaning I don't have any holes. So if I look for my vertical asymptotes, meaning my restrictions, I see that I have a restriction at x equals -1, and that will be my only vertical asymptote. Now again, remember when we are finding the horizontal asymptote, we compare the degrees of the numerator and the denominator. In this case, the degree of the numerator is smaller than the degree of the denominator. So remember, whenever that happens, we're going to approach 0. So we have a horizontal asymptote at y equals 0. Again, the reason why that's happening is if you plug in an extremely large number into this function, you'll see that since the degree in the denominator is larger, we're going to get extremely close to 0, because if you divide by a really large number, it gives you a really small solution. Okay, let's look at part C. So again, I'm going to start by factoring just so we can see what we have. And what I'm left with is this. So you're probably going to notice right off the bat that here I have one of those removable discontinuities. So I know that x cannot equal -3, but remember, if it's removable, it's not going to create a vertical asymptote. So I do have a vertical asymptote still at x equals 4. Because I still have this restriction left, and that means that I also have a hole at x equals -3. So remember, whenever you have a removable discontinuity like this, it creates a hole in your graph. So you do want to make note of it so you can remember to include that feature in your graph. Now let's compare the degrees. Again here, I see that the degree in my numerator is equal to the degree in my denominator. So that means if you plugged in really, really large numbers, essentially everything would cancel out except for your lead coefficient. So the lead coefficient here is 1. Here it's also 1. So that means I have a horizontal asymptote at y equals 1. Okay, for this last one, again, let's try to factor to see what we have. Okay, so after factoring, I see that I have 2 vertical asymptotes because I have 2 restrictions. So I have vertical asymptote at x equals -2 and at x equals +2. For my horizontal asymptotes, I'm going to compare the degrees, and what I notice this time is that n is larger than m. So this means that I have no horizontal asymptote. However, this falls into that really specific case where the degree on the top is exactly 1 more than the degree on the bottom. So that means I am going to have a slant asymptote. So here's how you find the slant asymptote. You're just simply going to do some long division. So I'm going to do my numerator, x cubed, plus 3x squared, and we can add some placeholders, divided by my denominator, so x squared, and I'm going to add a placeholder here as well. So I'm going to start dividing. Here I have x cubed divided by x squared, which is x. We're going to multiply going around, and then we're going to subtract. So this leaves me with 3x squared plus 4x plus 0. And I can do one more round. I do 3x squared divided by x squared, which is 3. And then I'm going to multiply 3x squared plus 0x minus 12. And then I'm going to subtract. So I have 4x minus 12. So here I see that I'm done dividing because my degree here is smaller than my degree here. So whenever you reach this point, the equation of your horizontal asymptote is always going to be this portion of your long division. So again, it is an equation. It's y equals x plus 3, which note is a linear equation that is slanted. It has a y-intercept at 3 and a slope of 1. So again, I don't have a horizontal asymptote in this case, but because the degree on the top was exactly 1 more than the degree on the bottom, I have this slant asymptote, which can be found by doing some quick long division. All right, that is all for today's lesson. Thank you so much for watching.